So I'm Dan. I'm here to talk about Heap and how it works under the hood and why it presents a particularly nasty data problem and how we use Postgres to power all the analytical features in our product. So a little bit about me. I joined Heap in July of 2013. Before that, I was at Palantir doing various backend analysis things. Before that, I was at Stanford, where I studied math and computer science and did a bunch of research on machine learning, which has nothing to do with this talk at all. So briefly, we'll cover what Heap is and why the particular way we've defined our web analytics product makes this a particularly difficult one to build. And we'll also talk about how the queries and the read path is distributed so that we can power it with more than a single node. And then we'll talk about how we make those individual subqueries, how we make the local queries fast using various Postgres tricks. And then we'll discuss how all the distributed systems operations work to keep all the data in sync. So I'll start with a brief overview of what Heap is and how the product works in a basic way. So Heap is a web and iOS analytics tool. The goal of this is to help you understand your users. That can be anything from what features they're using to how are users converting through various steps of the funnel to how many new users is this marketing campaign getting us, or if a person updates their profile picture within 4 days of signing up for our product, how does that affect the likelihood that 3 months later or 6 months later they'll still be using it? All sorts of kinds of analysis you'd want to do on a product. So there are a dozen tools that do something like this. They all work basically the same way. They give you an API where you log events, and then later you have all the events and you do whatever analysis you want, funnels, graphs, all that sort of stuff. So let's say we have a hypothetical travel booking website that's hypothetically called Airbnb, and you want to understand some kind of like a checkout flow or what percentage of users are buying a hotel or anything like that. So you're probably going to start with having an engineer on your team instrument the checkout button. You'll add a click handler to the book hotel button, and you'll log the booked hotel event. And maybe you'll go through the rest of your app, and this is your search results page, and you'll instrument viewing a listing and signing in and entering a credit card and all the steps that you think are interesting to you. And then, a month later, or 2 months later, or whenever, you'll have a question, something to the effect of, what percentage of our users end up booking a hotel? It's a pretty fundamental flow. You really want to understand this. So you run your conversion funnel, and you find out that the majority of people who view a listing end up booking a hotel, but only 4 or 5% of the people who sign in end up viewing a listing, which is an enormous drop-off. So you want to understand where they're dropping off. Maybe you want to add an intermediate step, like did they do a search or not? If they did a search but didn't go through the listings, maybe our search results page is not good. But if they're not even getting to the search part after they do the sign-in, then maybe we need to make that flow nicer. There's really strong product implications to whatever sort of thing you find. So you want to add some intermediate steps. And now you need to go get an engineer to log the thing and wait for it to pop up on their Jira as the top thing that they're supposed to do. Wait for that code to ship, wait for it to go through the App Store if you're on mobile, wait for your users to upgrade. At the very least, you need to wait for the event to happen enough in the world that you can do statistically meaningful analysis on it. So at the bare minimum, we're talking about 2 weeks of lag there, but in most practical contexts, you're talking about like months, 2 to 6 months, is a pretty common number that we hear at bigger companies. So then you get your results back, and you see there's like a drop-off somewhere between the sign-in and the viewing a search page, and all of a sudden you have 50 more questions you want to ask, and you got to go through this whole loop again. And let's say you spend a month on each, and it's currently November, and all of a sudden it's Q2 2016 before you have any answers, and it takes a huge amount of time to do this. And I think the actual result is that people don't do the waiting, they just don't use the analytics that they should be using to power their products. They just make decisions on gut, because it's just too much friction to do all this. So the point I'm trying to get across here is that analytics is, in a very fundamental way, an iterative thing. You never know what you want to be tracking up front. You don't know what you're missing. You don't know what your unknown unknowns are. The sort of state of the art for all these existing tools is to come up with what's called a tracking plan, which is sort of the Soviet 5-year plan equivalent of analytics, where we will sit down and think through all of the things that we will need and all of the stuff we will conceivably want. And obviously you have holes, and when you have holes, you have to go through this whole rigmarole to get the data you need to do anything with the data. So the Heap approach to this product, or to this problem, is to just capture everything up front, every click, every form submission, every page view, every swipe, tap, et cetera, whatever you want. Capture everything that users do and give you a way to analyze it retroactively. So when you want to add stuff to a funnel, you already have the clicks that have happened since forever, since you installed the product. So there's a snippet, you throw it at the top of your website, sort of like Google Analytics. It starts capturing all the stuff, all the clicks, page views, whatever. It goes to our servers. That'll show up as something like this, which you can't actually read as well as I was hoping. It's just a bunch of JSON blobs showing events that Heap is capturing. Clicks, and every click has a bunch of properties, like the path of the page and the text of the button that you clicked and the CSS hierarchy and session properties like the refer for the session and all kinds of tags and codes and all that stuff. So this flood of data is the first thing that's really hard about building Heap, is that we're capturing 10x to 100x as much data as any other web analytics product. And 95% of it you will never care about. Is a click on something that you will never be interested in analyzing, or it's just some, like I click when I scroll through stuff on Wikipedia that's like hundreds of clicks. You're never going to care about that. So we have all this data, and we want to make this something that people can use when they're not data scientists or engineers or something like that. So we have a tool we call the Event Visualizer, where it shows you an overlay of your website, and you do an action, and it extracts from the action you perform what the definition of that event is. So you'll click this sign up button, and that'll bring you to a screen like this, where you can define an event called sign up, and you hit confirm here, and now you have a human usable event called sign up, and you can twiddle whatever properties you want, like limit it to this page, other various CSS things, and now you can use this elsewhere in the analysis. So later on, if you want to graph something or something like that, you use those events to build up your analysis. So that analysis includes graphing, your basic temporal graphing stuff. Here's an ad hoc query where we're doing clicks on a like button filtered for country of Canada, and maybe it's totally plausible that this is a thing that we want to use. Heap supports all kinds of ad hoc grouping. So here's signups grouped by the plan that they signed up for, or you might want to group by source of the user or any kind of thing that you want to do an ad hoc grouping on. There's the funnels, as I mentioned before, any kind of conversion, add a bunch of steps arbitrarily, remove steps, add filtering on it, add grouping, all that kind of stuff. Retention is another really common thing our users want to do. So show me the percentage of users who signed up in this week who did at least one login in each of the following weeks, and what is the percentage that are still around 3 months later, 6 months later, that kind of thing. Behavioral cohorting is another important one. Maybe I want to define a segment that we call active users, and we'll say that is users who signed in at least 4 times in the last week and did at least one friend request or accept friend request, which is a very active user. But maybe you define a segment like this, and then you can track the membership in it over time, or you can filter your other analysis on it, like group that funnel to only include our active users or people who are not our active users, all that kind of stuff. So the point of all this is that the analysis that you're doing is very rich and pretty open-ended and almost totally ad hoc. Any kind of filter you want to add, any grouping on anything we capture, we can do that at query time. It's way beyond our usual pre-aggregated graphs. It's funnels and retention and cohorting and all that kind of stuff. So the usual, like the Google Analytics approach of just pre-aggregating all the things that you want isn't going to work here, because we want to make it possible for people to iteratively drill into this stuff and make that iteration really fast. And then sort of the cherry on top of the challenge is that it has to be pretty real time. There's a lot of use in this product if you have data that's like 24 hours of latency, but there's a lot of additional powerful use cases we want to enable that really require the data to be like within minutes of real time. So these are the core things that make it really hard to build this product. So let's talk about the data scale for a second, just to give you some vital stats. We're talking about 60 terabytes of data on disk right now, so not the hugest data set in the world, but growing really quickly. That's 80 billion events on 2 billion users. We've been active for about 2 years, but the usage kind of does this, so that biases towards recency. Around 3% of it has been in the last week, and there's a couple, any day now, a potentially large enterprise user can sign on, and the usage does that again. And so the scale is too huge. The point I'm trying to get across here is that we're way too big to scale up. This is not a problem that we can solve by paying for a big enough single Postgres instance. We need some way to scale out, some way to parallelize the reads and scale out that analysis. So this is where CitusDB comes in, and I'll start by walking you through the sort of schema that we use within Citus and how it handles that and how it handles sending out these queries and all that stuff. And then I'll get into how we make those queries fast at the local layer. So we might want to start with something like this, which is that legible at all in the back? Cool. So we want to start with something like this, which is a massive single table of users. Every user has a customer ID, which is the ID of the customer of which that user was a user, and also a user ID within that customer, which is your end user ID, some random 53-bit number. Every user should be able to have a handle, which is a globally unique tag that we allow you to give those users, and I can get into later what that's for. And finally, for every user, there should be an unstructured JSON-B blob of whatever properties we want to attach to that. So that can include core stuff like what the referrer was that caused the user to join for the first time, or it can cause it can be customer-specific stuff like age or name or any kind of custom A/B test variant, anything you want to attach to that user. And similarly, we'll want a similar table for events where every event should belong to a user. It has a customer ID and a user ID, and every event has a time, which is the timestamp that the event happened at. And that event should be able to be represented as a similar JSON blob where it includes all the core stuff like CSS hierarchy or the page path or the text of the button that led to this click or whatever else you want. But it also should be able to include all kinds of custom stuff like custom session level properties or whatever else you want to affix to this data. And as I annotated at the bottom, there should be a foreign key between those tables, at least morally, because the events always belong to a user and the user has to exist. So your data might look something like this, where here we have 4 users. Each one has a customer ID. There 2 of them belong to customer 1, 2, 3, and they have some various handles. 2 of them have A/B test groups on the right. 1 of them has an email listed. These are sort of the users that we want to talk about. So within Citus, we're going to distribute both of these tables by that customer ID, user ID tuple. That's your global, that uniquely identifies a user. So we'll shard this table by that pair, and we'll shard our events table by the same pair. And we'll, if we set this up in a way where the shards all align, like the shard boundaries are the same between those 2 tables, and we keep the underlying tables co-located, Citus is really smart about how we do the queries. It'll make all the joins be push-down joins. It knows that you don't have to do any actual distributed joins, move any data around. So to give you a visual on how that user table gets sharded, maybe we'll have 2 shards here, the users 001 and users 002. And Citus knows, for example, that users 001 has customer IDs between 123 and 678, which you can't quite see there. It's the 3rd row. And users 002 has only customer ID 756. So when we want to run a query on this, like get the number of users and group it by the A/B test variant that they saw, Citus is smart, and it knows that it doesn't need to run this subquery on the second table because on 02 because there can be no users on that table that have customer ID 123. So it'll run the one subquery we need, and it's really, that subquery is just a vanilla regular Postgres query. And then it'll run that, reassemble the results, give us the result. So from the perspective of a client of this, we're just running a regular Postgres query. In fact, it's wire compatible for the queries that are allowed. Yeah, so, question?
Good question. How many users do you have working?
Around 2 billion total, and around 80 billion events across those users. Yeah.
Across how many customers?
Across between 4,000 and 5,000 customers. So, but there's a strong power law component to that. Like most of them are really tiny, and then there's some, 1 or 2 or 5 massive ones. So this is your basic story for how these queries are going to get distributed. Let's walk through briefly an example of one of those kinds of analytical queries we might want. So let's say we want to do a graph of logins, which is some event that we've defined, and filter for enterprise code for users that have an enterprise code. And enterprise code is some custom property that the customer decided to pass in, and is defined is just UX for is not null. So we'll build this up piece by piece. First, you'll have an event piece of it, which is get the rows from the events table where the customer ID matches this thing, and the time is between the time range at the base of that graph. And the event type is login, which is the type that the user wanted. And then we'll have a user query as well in the user table where we'll look for users from this app where the enterprise code is not null, and that's how we'll evaluate that filter. And we'll stitch them together with an inner join so that this gives us exactly the thing we want, the logins where the user, where the enterprise code is defined. And at the top, we can group it by the day that the event happened so that we get the time bucketing, and this gives us our number for each part on that graph. So this kind of gives us the full query, and what's really neat here is that Citus is smart enough to evaluate this semi-complicated join with a bunch of local joins, because it knows that there's a really small number of actual shards that are relevant to this query that have customer ID 123 data, and all of those user shards and event shards are co-located with the same shard boundaries. So it can just do local joins on all of our worker nodes and reassemble the results and give us the results. So this is our distribution story in short. Every customer has a customer ID. Every user has a customer ID and a user ID. There's one massive table of users and one massive table of events from that, or at least that's what you see as a client of this. And then internally, all of those are sharded by customer ID and user ID. And all of the kinds of analysis that we're going to want to do shard by user. The funnels, the graphs, all that stuff can be distributed at the user level. We don't ever have to do any joins that aren't push-down joins. So we query this like a regular vanilla Postgres instance. Citus comes up with a bunch of subqueries that it runs on the workers and reassembles the results, and it handles failover if one of those workers is down or something like that. And since those subqueries are just vanilla Postgres queries, we can use all the kinds of tricks that we want from regular Postgres tuning to make them fast. That means whatever indexing we want, whatever schema tricks, all that sort of stuff. So if you're familiar with partitioning in Postgres, like partitioning a table, this is a shorthand. This probably sounds pretty familiar, and a shorthand way to think about this is Citus is table partitioning, but the partitions can be remote. Or I guess correspondingly, if you don't know what table partitioning is, but you just saw this talk, then you can think of partitioning as this, but it all has to be local. So this is the mechanism by which we can reduce a big distributed query into a problem of tuning individual, like regular vanilla Postgres queries. So how do we do that? So here's that example where we're looking for logins where the enterprise code exists, and we're grouping by the time so we can get our temporal graph there. So maybe for this, it would be pretty easy. The thing that's going to dominate the query is that events table scan, because the events table, even the sub shards are going to be large, because it's all the events, all the clicks, all the page views that are happening on that app for a certain range of users. So maybe for this one, we could just come up with an index on the type field within the data blob, because this is like pretty bread and butter gin use case. But this is kind of a toy example, because usually you're talking about like the point of Heap is that you should be able to define an event based on whatever stuff we're already capturing and do a retroactive thing. So if I want to be able to define an event on a CSS hierarchy and a page path and a refer and all that stuff, and have it do this kind of query. So maybe a more complicated one would be, let's say we have that checkout button from before, and we define the confirm checkout event to be a click on a button where the text is confirm order, and the CSS hierarchy matches this glob pattern where there's a div with checkout modal, and then there's an A tag with a button inside of it, and the path of the page is /checkout, and it's a click. That's the type of the event. So this is not a thing that we're going to be able to solve with a bunch of indexes on individual columns in that data blob. Like, we're not going to be able to bitmap join our way, or to bitmap scan our way to solving this kind of query, especially when we have that sort of regex on the third row. But a thing that we can do is there's a tool in Postgres called partial indexes, which if you haven't heard of them, a partial index is an index where there's a where clause attached to it. So any rows in your table that match the predicate in that where clause will be in the index, and anything that doesn't match that will not be in the index. And the thing that's really neat about partial indexes is that the query planner is really smart. So if you do a query and you're filtering for the path, the action, the CSS hierarchy, and the text equal to those exact, with this exact predicate, and you have a partial index that matches that predicate, the query planner is smart, and it knows that I can just look in that partial index for exactly the set of rows that fit this. And then all I have to do is the time grouping and possibly filtering on the customer ID, depending on how I set up my constraints. So this gives you a partial index that looks something like this, where you index the time field on the events table, and you filter this for rows that match exactly that predicate that we had before. And those we know those predicates up front because you're always defining that event and then using it. And then if we want to evaluate that query, we can do a single scan through that index from time A to time B, and we don't have to worry about any of the other stuff. And it turns out that this works really well, and the reason is that those event definitions are extremely sparse. Like Heap is capturing an enormous diversity of stuff, clicks all over your website, page views, swipes, taps, all that kind of stuff. And the percentage of those that actually are on a particular button or views on a particular page is going to be vanishingly small, especially for large apps, which is the ones that have the large data, which is what makes this hard. So, maybe to make this a little more intuitive, the percentage of clicks on your website that are on the checkout button or on the confirm order button is going to be 1 in 1,000, 1 in 10,000, 1 in a million, depending on how well we've optimized that website, something like that. But a very, very small percentage of things. So if we use these partial indexes as whitelists to the rows that we care about, we can do this scan incredibly quickly. So this is the basic strategy. Every event definition that you do in Heap is just a filter on that events table. And under the hood, Heap will maintain a partial index for each of those filters, which will index exactly the rows that you care about. And the variety of events that Heap is capturing makes all of those really sparse so that it's a really tiny percentage of your table that you actually have to touch at read time when you want to evaluate one of these queries. And this really fits quite nicely into this whole idea of retroactive analytics because we don't have to maintain a dynamic table schema. Like we don't have to do, create a separate table for the checkout button event and maintain that and keep the data in sync with the base analytics table and all that stuff. All we have to do is pop an index on this, and nothing ever modifies the underlying data. And as long as we keep, we do one single index creation and over the whole table, and then we have the event, we're ready to go.
One question, do you run into issues where you've got 10,000 indexes on this one table?
We do. So that's a really good question. So the underlying tables, the underlying shards for any large customers are going to be specific to a particular customer. So only that customer's data will live on that shard because we're sharding first by the customer ID and then by the user ID. So you only need the shards you only need the indexes that are relevant to that customer. So you still do get, for particularly active customers, you'll get hundreds or maybe small thousands of partial indexes per table. And we do sometimes have to wrestle with the query planner to do the thing we want. But that's all happening without reading a massive data set from disk, so it turns out to be net preferable. But it's still something we're kind of working on. So this kind of gives us our story for how we do basic graphs and basic reads of these events. But the analytics that we want to power are much more expressive than this. We want conversion funnels, we want retention, cohorting, all that kind of stuff. So you can do all of that in this model. And in fact, it fits really nicely into this relational model because all the things that you're doing in Heap are your standard selecting, filtering, grouping. It's really nice that we can use that basic relational framework in this. But this turns out to be really slow. For example, if you want to do a funnel between, let's say, signed in, viewed a listing to booked a hotel, and we'll call those steps 1, 2, and 3 in a funnel, you're going to have to do a bunch of self-joins, and that's going to become a whole thing. And it turns out we can do a lot better than this if we write a UDF in C. And I say we, but the Citus team really did all the work here, so keep that in mind. So let's say for a funnel, for example, we want to evaluate this kind of thing quickly. So all of the analysis breaks down at the user level. So if we use those indexes to dynamically create an array for each user of the sign-ins, listing views, and hotel bookings for that user, and then pop this into a UDF, we can do a single scan and do this funnel evaluation really quickly. So to be a little more concrete about what that might look like, you can create a C extension, we'll call it funnel events, that takes an array of events where the integer is the step in the funnel that it is. So that's 1 for sign-in, 2 for view to listing, and 3 for hotel. And we'll also take the number of steps, and it'll pop out an individual funnel result for a user where there's 1s for the steps that the user did and 0s for the steps the user didn't do. So for example, if I'm doing a 3-step funnel and the user did 1, 2, and 3 in that order, we'll pop out 3 1s because the user did the full funnel in order that we care about. But if they do 1, 3, 2, 2, 2, then they'll only actually convert on the first 2 because they did the 3 before the 2 and we want them to be in order. Or similarly, if they just do the first event and they don't do any other stuff, then it'll be 1 with some 0s. And for users that don't do any of these events, they won't actually show up in this because they've already been filtered out by the query planner. So this turns out to be something that we can do that enables us to do those funnels, and this kind of generalizes to other kinds of analysis we want to do incredibly quickly. So to be a little more concrete about what a query might look like, let's say we want to do a 2-step funnel from viewed and item detail to confirmed in order. That'll turn into one single scan, sort of like the graph view on the viewed item detail event, and another one for the confirmed order event. And those are both really quick partial index scans. And even if we do an 18-step funnel, that's still a very tiny % on net of our data. And we'll put a union there and sort them by the time and aggregate them into one array for each user that we're talking about. And then we'll pop that funnel events UDF on top and sum it up, and this kind of gives us our full funnel. So again, the analysis all shards by the user really cleanly, and we can just run this query on each subshard, and the Citus distribution planner is smart enough to know that all these unions and all whatever kinds of weird joins and lateral joins, whatever kind of stuff we want to do, Citus knows that it can do all of those things locally, and in fact, it does for us. So if we wanted to extend this, for example, add a bunch more steps to the funnel, we can do that totally natively. We just add more steps to that union, more partial index scans, still stays fast. Maybe we want to filter for, add some filter on a user level property, like filter for users that signed up before this time, or filter for users where that enterprise code is non-null or something like that. We can just add another join to the bottom and we do a single query on that users table, and we can index those properties because they're all individual strings. And all the joins are going to happen locally. We'll get a really small result from those because they're all aggregations. You'll send it all back to the Citus master. It'll be a really small net amount of data because it's all aggregations. We're all talking about numbers. Like an 18-step funnel is going to be 18 total numbers that come from the subquery. And this kind of gives us a result. So, that's too far. So, so this generalizes really nicely to all the kinds of analytics that we want to do because it always partitions on the user. So we can, for any kind of family of queries that we want to do, we can add a new UDF that matches the analysis that we want to do. So we can add one for funnels and one for retention queries, and you can kind of imagine how that would work. Like you want to get users and see which ones logged in at different weeks after they did the sign-up event, and you'll just grab the sign-ups and the login events and pop them into an array. Like it perfectly well generalizes to that. Or all the cohorting that you want to do, you're only talking about one user's events there, and it generalizes pretty nicely. You can make those UDFs in C. You can make them really fast and tune them. That's kind of how this all works. So your meta formula is you're doing a query. There's a relevant set of events. You build up an array by scanning all those partial indexes. You get your custom array of events. You pass that into your custom UDF. And then you can do arbitrary joining, filtering, grouping, whatever else you want to do, just totally natively relational, because that's the model. So Postgres makes a lot of this really nice for us. It handles a lot of the, all the sorts of ad hoc interactive analytics that we want. It's not perfect for us. We do have a wish list. One thing that's really problematic for us is maintaining all these partial indexes. And even though they're usually very small because they only touch a small percentage of our table, running them online is still a pretty substantive amount of CPU and I/O that go to these. So ideally, we could build these from existing indexes. So for example, if I came up with an index, if I have an index on the page view path, and I want to make a custom, I want to define some event where that includes a page view path filter, we could start from that, and we have a very small subset that we're already scanning over, and we could make those partial index creations a lot faster. Another issue we have is that you want to do these index creations with concurrently, because you don't want to muck with the writes or make writes hang or anything like that. But you can't do create index concurrently. You can only do that. That serializes along a single table. So that makes it really hard for us to use this and adds to more headache. And another issue that you brought up with that question is that this is a kind of pathological use of the query planner. We're talking about tables with thousands of indexes maybe, and there's an exact index that fits the filters that we want to do. So if we could just tell the query planner the thing we want, morally, I'm totally on board with not having hinting because I think it's the good thing for the long-term health of the query planner. But like, we're talking about multi-second. I'm going to get egged in a second, but we're talking about some occasional multi-second query plans here, and it might be kind of nice if we could we know the plan that we want. We always know exactly the plan, and the stats collection for the JSON is kind of still being figured out too, so don't hate me. So just throw it. No, I'm kidding. So yeah, so this is your basic story for how we handle turning a big query into a bunch of small distributed queries and reassembling results. But this is a model for how you do the queries, but not really a full distributed system. Like this leaves a bunch of questions open. One of them is that when you shard by that user ID instead of the time range, your shards are all being written to all the time. So if you want to move shards, for example, or let's say you're decommissioning a machine, you want to move shards off of it, or you just want to create more replicas of a shard because you're increasing your replication rate. All the regular distributed systems operations that you care about are non-trivial, at least when you want to shard that way. If we sharded by time, it would be really easy because most of the shards would be static and we could just move them in the background and that kind of thing. Another issue is that you're definitely going to want to have something between your web-facing, like a load balancer-facing servers and the underlying DB. You want to be available when the DB is down, that kind of thing. You need some sort of queue there you want to handle ingestion spikes by going into some queue there. So if it wasn't obvious from the description, the way we handle this is mostly with Kafka. So we use Kafka as a short-term commit log, and Jay used a line earlier, Jay Krebs used a line earlier that Kafka is a commit log for your data center, which I think is the exact perfect way to think about this.
The web JSON object goes straight to Kafka.
Yes, exactly. So you'll hit an endpoint, and it'll a very dumb node process will just dump it right into Kafka. It'll sit there. And then on the right side, we've written some custom PGSQL to handle making those message insertions into Postgres idempotent and commutative. And it turns out that that's a really valuable thing for anytime you have any kind of distributed system. When you can make messages idempotent and commutative, you're going to make your life a lot happier. So we have some custom UDFs for this, so that you're not doing vanilla inserts and updates. You're calling some custom function like upsert a new user or upsert a session, and it'll make everything commutative and handle all that for us. Another thing that's really nice is that this is kind of when we were first reading about this, we thought it was kind of a weird design decision, but in Kafka, in the underlying API, the consumer determines its own offset. So you don't say, send me data from this topic. You say, send me data starting from this topic in this partition, starting from this offset. So the fact that the consumer has to manage that, there are APIs that exist that paper over this, but the fact that you can manage that means that replays are very possible, in fact, pretty natively supported. So if you're not familiar with Kafka, I'll give you your 30-second what is Kafka overview. Kafka is a distributed, fault-tolerant, persistent queue. The messages are sent to topics. The underlying topics are split up into partitions under the hood. The partition is your unit of replication. The partitions are replicated. Kafka is also another really nice feature of Kafka is that it preserves order within those partitions. So each partition has a single master, and all the writes go through there. So that turns out to be really helpful for us, even though this stuff is commutative. It's nice to be able to assume that in some cases. And then every partition you can think of as a big, or like indefinitely growing array, and every message has an offset, which is you can think of as the index within that array. So you're only appending to those partitions, which means that your writes are always append only and streaming on disk. Like this partition maps to a set of really long files that just index 0 through a zillion womp right in disk. So the fact that this is all append only and all your reads are scans also means that you can run this on spinny disks and it'll still be really fast. And the persistence is native. You can, like this is not a queue that has stuff in memory and then emergency flushes stuff to disk. This is very natively persistent, and that gives us a lot of really good guarantees. Like we can use it as a commit log for all the data that's coming in. So, and this is your one picture summary of what Kafka is. There's a topic here with 3 partitions, and they're all growing, and there's writes coming in to the end of each one, and somewhere there's a reader that's scanning forward on each one. So as I mentioned, this gives us the persistence, the message ordering guarantees, the fault tolerance, this really fast streaming of stuff into whatever processes we want. And then this is your set of blobs that are how this is all kind of wired together. So on the left, you have a big Kafka cluster with a bunch of partitions. N is actually 30 for us right now. For each partition, there is a corresponding queue processing process, which is a Scala ACA process that pulls stuff off a partition and calls those custom PGSQL upserts to move the data into the actual Citus workers. And those queue processors talk to the Citus master to determine where the actual blobs belong for each of the blobs that we get. So they can write directly to the underlying workers, which is great. We don't have to stream everything through the Citus master. And as I mentioned, in Kafka, the consumer manages its own offsets. So this is really important for us. It means that if one of those queue processors die, like we have those writing all the time where they are, like we have them writing all the time in Zookeeper where they are in each partition. So if one of them dies, we can pick up right where it left off. Another thing that's really important is we can know at any time where we are in these. So the distributed systems operations that we want to do, the fact that Kafka is holding our data for at least a couple weeks, we have it retaining for a month, means we can sort of replay stuff, and the messages are idempotent and commutative, and that means we can do the sorts of distributed systems things we need. So I'll walk through one example a little bit more concretely, and it kind of generalizes to all the stuff that we end up needing. So let's say I want to move a logical shard from Citus worker 1 down to Citus worker M. That shard is just a table. It's just a regular vanilla Postgres table. And there's writes potentially coming into it all the time. And you don't want to have some global lock where you block writes to that table because nothing else in your backend likes that. And it turns out to be a huge headache. So ideally, we could just copy the table from worker 1 to disk and rsync it over to worker M and read it in there. And now we have a table. We have a new replica. Or like, ideally, this would be the whole system. But you're going to miss writes because while you're doing that copy, writes are coming in to that shard all the time. So a slightly nicer thing that we can do, and I'm papering over a lot of details here, and if you're interested in this kind of stuff, definitely come talk to me after because it turns out it's like super cool. But the basic high level of it is we have those offsets all the time in Zookeeper that that's a lower bound of where we are. So we can guarantee that anything below those offsets is already represented in our data. So your basic formula for how you do those kinds of operations or how you move that shard looks something like this. We start by taking a snapshot of all of the partitions, what the current offsets are in Zookeeper. So that's where all the queue workers are right now, or the queue processors. Then we'll copy the shard and move it over, and then we will add, so that's your standard dump restore of a table, and I think we actually use SCP, but whatever you want. And that'll move that table over to worker M. You'll load it in as a regular Postgres table because everything's vanilla Postgres under the hood, and we can use all of our regular Postgres toolchain. And then we'll take our second snapshot of the offsets that are where we are in Citus and or where we are in all those Kafka partitions. And then we have a range because for each partition, we now have a lower bound and an upper bound offset for what could possibly have been missed. And all those messages are idempotent and commutative, as I mentioned. So we can just like Kafka, it's a single scan in Kafka. We can do a single scan on each partition to replay the stuff that we potentially missed and call into those UDFs that we have. And now this is like the details kind of fall from there on how you move a shard live without locking anything. And that's how you kind of turn this into a real distributed system. And then the other stuff that we kind of need to do follows a similar basic formula. If you want to create extra replicas of a shard, if you want to split a shard, which is a common one that we have. And you can imagine because if a customer grows really quickly, then their shards are going to get really big, and you want to split those up into more sub. Oh, that's a microphone. So on the read path, the Citus master is just storing metadata on where the shards live and what their boundaries are. But then on the write path, you're just running a single Postgres, or sorry, on the write path, I don't know if I did that backwards. On the write path, your Citus master is storing what the metadata is. So a message comes in from partition 2, and I need to know where it belongs in the underlying workers. And I have the metadata from the Citus master, and I call that UDF directly on the workers. But then on the read path, we don't have to think about anything. The master just does all the work. We just run a vanilla regular Postgres query. It'll farm out the subqueries, get the results, reassemble them, send them back to us. Does that make sense? Cool. Yeah, I just realized I was not repeating questions. Someone's going to yell at me later. Yeah, but this is our basic, oh, go ahead.
I guess I had a question about the nature of how you made these UDFs idempotent and commutative.
Mm-hmm.
Can you speak to that?
Yeah, sure. So I guess I'll get into a little bit of detail. The one thing that makes it really hard for them to be commutative is that the tracking scripts that are on all of those websites and iOS apps they currently send normalized event data. So they're sending session page view event instead of the event having all the page view and session properties glommed on. But in the schema, you really need all that stuff in the event blob so that you can just have that single partial index have all the things that you need. So this is kind of the balance that we're striking between fully normalized and fully denormalized. But you need, for example, your page view path to be on your event so that you can use it in a filter like that. So you need to do some work to make, if a page view and an event come in at different times and the event corresponds to the page view, you need to make sure that event gets its page view properties, or depending on whichever order they come in. So the actual answer is just, it's a regular vanilla PGSQL function where we do an upsert, plus we make sure the user exists so that we can actually maintain that foreign key. It's a bunch of regular Postgres queries. You'll do an update if a page view comes in where you update. We have an index that for each page view gives you all of its events, and you do that update, that kind of thing. Does that roughly make sense? Cool. So yeah, so this is how you kind of turn a sharded Postgres setup where you're writing to the shards all the time into a distributed system that can actually work in the real world. Say again?
Can you throttle Kafka on the outbound side?
On the outbound side.
So the events are coming in, you're recording them, but you're throttling what's going in the first.
Yeah, we can kill. So we actually have PG balancer in front of them, so that we can do whatever we want. But those queue processors are our code. We can do whatever we want.
You look at RabbitMQ instead of Kafka.
We did. The question was, do we look at RabbitMQ? The persistence guarantees in Kafka are great, and the kinds of the native persistence here is so powerful for us. It means we can do all these replays, and it's not even a hack. It's like a thing Kafka expects. Yeah, super cool. I'm a big fan. Kafka is my second favorite data system.
When you replay messages in Kafka, do you change the offset of the existing processes, or do you add new processes to the new shards?
Oh, that's a good question. The question was, when you do a replay, do you change your offset so that you start back from there, or do you add an additional queue processor that does a second scan? We have a separate. It's actually, we call it a backfill processor, but it's a separate process that just does a single scan, because you don't want to back your whole ingestion up to do, because you're moving shards all the time constantly. You're constantly switching out your hardware, that kind of thing. Yeah.
So when you're doing, back up. Why are you storing the offsets in Zookeeper rather than actually in Postgres?
The question is, why store the offsets in Zookeeper instead of Postgres? You could store them globally in the Citus master. It makes us a little bit more fault tolerant to not do that.
It seems like then you're doing like dual writes. You're writing in Postgres, here's some data in Postgres. Oh, and now I've written that data, so now I have to update Zookeeper with my new offset.
Yeah, I mean, you're keeping track of different kinds of state. The writes to Postgres are the underlying actual data messages, and the Kafka offsets are purely metadata. You're talking about, maybe 1 or 2 writes per second per queue processor to Zookeeper, which is a trivial amount. And we have to have Zookeeper anyway because it powers the Kafka. So.
Can you do a replay on Zookeeper? I assume you could do some kind of a notion of a replay and that's why you're using your upserts. Can you do that on a time base instead of on a...
Can you do that on a time? Yeah, the way we would do that is the question was, can you replay on time instead of on Kafka offset? We would just convert that into a Kafka. We would come up with some lower bound where we know anything from the last 10 minutes has to happen after here. And everything's idempotent, so it doesn't matter if it's kind of sloppy, we can do the scan anyway. Yeah, idempotent stuff's great. Highly encouraged. Yeah?
How do you deal with node failures inside of the cluster?
Yeah.
How do you bring up a new node?
This is an excellent question. The question is, how do you deal with node failures in the Citus cluster? So the underlying shards are replicated, so on the read path, there's really nothing that you have to do. The hard part is, how do you keep the stuff in sync? So one way that we handle this if a node completely dies and we're all on EC2, everything's on EC2, so that has happened, is you can just bring up a new Citus worker and you'll temporarily have a lower replication factor on all the things that were on the old one, and then you can use this kind of process to rehydrate a new replica of each shard on the new machine. This works a slightly hairier case that we're still actually kind of figuring out what to do, and if you have thoughts, we should definitely talk after, is what do you do if one of those Citus workers gets really slow? Because if it dies permanently, then it's gone, but if it gets, often in distributed system stuff, something being slow is harder than something just outright dying. So in that case, we have hacks and headaches, and we should talk if you have thoughts. It turns out that one reason this is really tricky for us to handle, I sort of glossed over this for this talk, but every user in Heap, I don't know if you remember from the schema, we let you attach a handle to that user, and that's a globally unique handle within that customer. So if 2 customers get the same handle, we will merge their records under the hood. And you care about this because if you have, let's say you have logins on mobile and also on web, you want to merge those user records so that you can track like a common, you want to be able to track conversions across those, like people who downloaded the app and how many of them actually opened it within the thing. So those merges are happening on you're taking user A and merging it into user B, and those can be on different shards, and they can actually be on different workers too. So you can't just put a queue in front of each worker and have it be slow and catch up later. So we can talk later. Anyway, this is basic outlines of how Heap works as a distributed system. There's a lot of stuff that is still in the future work, blueprinting, figuring out how we want to do this phase. One of them is, if you've ever worked with analytics data, you'll know that there's a very strong hot, cold, medium component to it, where the overwhelming percentage of your queries, or the overwhelming amount that you care, is going to be on the recent data. Like for us, over 90% of the queries touch only the last 2 weeks of data, and we're storing all kinds of historical stuff. So it would be nice if we could do some kind of time tiering where we split out the recent data onto nicer hardware, but it's actually kind of tricky in our schema because we're sharding on the user, and you need a full user's record for those 10% of queries that touch all the historical stuff, because you do want to be able to do like 2-year retention or big, massive conversion funnels. So we have some thoughts, but we're still kind of figuring out how we want to do that. Another obvious short-term extension of this is that there's just way more analysis that we want to be able to do. That includes numerical stuff, that includes averages, that includes histograms that are really nice, and sketching algorithms that can be distributed, and mins and maxes and all that stuff. This is incredibly important for an analytics tool, and we don't even support it yet. I'm talking about like you can't, there isn't really a good way to do average revenue per user in Heap, which is or revenue divided by ad campaign. These are really high-level important things you want to do.
Tease the data off Kafka and start running it through some kind of archival long thing, sort of like you do that in RabbitMQ.
Oh, you're talking about the.
All of a sudden you have 2 copies, one going to the one that's not forward fixed.
Yeah.
Different hardware, different.
The question was, can we do the time tiering by just having separate clusters and having the fork at Kafka? Something like this is probably what we'll end up doing. One tricky piece of this is that ideally, like if we could, the historical stuff doesn't actually have to be necessarily totally real time. So if there's a way we can take advantage of that, then that would be very valuable for us. It would mean we could use much cheaper machines. So yeah, we're still kind of figuring out how we want to do this. But
We're using CitusDB as well, and our data is partitioned or sharded by timestamp, so that's a little bit different than what we're doing. But what we ended up doing is, so for each shard, we know what time range it covers, and then we have a process that moves stuff to a slower table space. So we have a fast table space, a slow table space, and then we just set development enables that table space on the individual fields.
yeah, the question or comment was, basically, if you're sharding by time, then all of this is a lot saner, because in your 99% of older data, you're not writing to the shard anymore because that time window is already over. So the distributed systems pieces are easy. You can just move stuff around like regular Postgres tables. You're not actually writing to them. The time tiering is really easy too, because you can just move them onto worse hardware over time, and all of it gets nicer. But in a pretty fundamental way, our data model doesn't really make it possible to do that, because you need to be able to do a funnel over the last month or 6 months or year or whatever of data, or just a graph. You want to be able to show, like some of our biggest customers are e-commerce sites for colleges, or for college students, so you buy textbooks there and stuff, and they need to be able to do this September versus last September. That's the kind of, so anyway, let's hang out later. Yeah, so we want to be able to support all kinds of numerical stuff and richer analysis, path analysis, more powerful behavioral cohorting, data pivoting. You should be able to do immediately from a funnel, show me the users who dropped off at this phase, or whatever else you want to do, or graph the conversion funnel percentage over time, or all that kind of stuff. And then from the actual using the data perspective, there's a ton more stuff on our plate that we would like to be doing soon, like alerting. I could set up this flow. You'll notice that in doing this analysis, you never had to write any code. It was purely clicking around your own app and defining events that way and using them. So that's incredibly powerful. It means like people who are not engineers can use this product readily. Like marketers, anyone can use this thing. It would be really nice if you could do more with those events. Like if I could do alerting, for example, set up an event that's the sign up button and ping me in Slack via a webhook every time someone does that thing. Or alert me if this conversion funnel percentage goes to 0 or low because we have a bug, or all kinds of stuff like that. Or live stuff. We don't actually do any live updating dashboards. This is would be really neat. So there's a lot of really powerful stuff that you can do with this data that is but this is the fundamental infrastructure that I think is going to get us there. It handles all the kinds of analysis that we need. Yeah. So I have a couple minutes left if you have any other questions, or you can find me on Twitter. I'm Dan Loves Proofs. I was a math major. So yeah, I have a couple minutes if you have any questions. Yeah, that's a good question. Is, do all the partial indexes hurt write performance, which is like the immediate question that you should have when looking at this. So remember, all those partial index filters are very sparse. So you're not actually writing to those indexes. For most events that come in, you're not writing to any of those indexes because it doesn't match any of the, even if you set up 1,000 or 100 or 1,000 or something events on your site, most events that come in are not going to match anything. So you're only writing usually to the core table and maybe to 1 or 2 indexes. It does hurt the write perf in the sense that you have to run that predicate on every event that comes in, which is kind of the minimum amount of work that you can do for this kind of schema, because you have to check at least once ever that that event matches any of the things that you care about.
Using probabilistic filtering between Kafka and the database, so you're actually just sampling and doing sketching.
Yeah, the question was, have we done any probabilistic filtering kind of stuff? We have some basic sampling, like you can speed up your queries if you toggle a sample thing. We would like to be, so we don't use HLL or any of that stuff for the distinct counts or anything like that. Since we're sharding on the user and a user can only be in one shard, maybe you don't necessarily have to do any of the distributed parts of it. We'd like to be doing it for sure. Like, we'll definitely need a sketching thing for the histograms. If we want to have a dynamically ranged histogram, we will need to come up with some kind of probabilistic thing there, or use one that's open source. Oh. Right. Right. Yeah. Yeah, the question is more around, like, can we send sketches of this stuff to Postgres instead of sending the raw underlying data? But as Colin pointed out, you lose a lot of the retroactivity that way, because you have to know up front what the filters that you care about are. Yeah, so making this retroactive and, yeah. So I mean, we're basically, we're optimizing really heavily on the querying and indexing power of Postgres, and that lets us support all the kinds of things we want and all the rich analysis that we want to do in a really fundamental way. But we lose the basic distributed systems pieces of this, and we have to sort of do all that ourselves. And the fact that we have to be retroactive, and we also have these really sparse events that we want to filter for, and we also have advanced cross-event analyses that we want to do, like conversion funnels. That's why we can't use, H-based Cassandra, something that natively distributes. The question is, can you do cross-customer queries? You can't, and that saves us a lot, because every query that comes in will have a single customer ID on it, and the Citus perfectly prunes the subqueries, and most of our shards only have one customer of data. Yeah, I mean, we never expose a customer's data to another customer, so there isn't really any way. Yeah, so the question is, can we just create separate, like a separate instance, separate Citus cluster for each customer? But the largest customers are going to be a non-trivial percentage of this. So one thing we've played with, and we're still not sure how we want to do this, and if you have experience with something like this, you should come talk to me. We might end up doing something to the effect of take our biggest mega customers and move them on one cluster so they don't disturb everyone else, and take the bottom 99% of customers in terms of size and move them somewhere else. But a simple thing where you just shard for a different single Postgres instance for each customer isn't going to work. Yeah. Okay. Yeah, the question is, how nearly real time is it? We're currently sort of straddling 2 different infrastructures, which is this and some legacy stuff. For the legacy stuff, it's bad. It's like often midday, upwards of an hour of latency. For the new one, we think we can get it down. I don't want to make any promises, but to like very fast, like minutes or sub-minute. I think I'm out of time. Thanks.